Hello, good day to everybody. Now, do you know what an earthquake is? And do you know why earthquakes occur? Now, if you want to know more about this phenomena, then you should watch this video. Please subscribe to my channel, The Science Guy, and click on the notification bell so that you will be updated of my future videos. So, okay, now let's watch this. Hello, greetings. Now for this lesson, we will be focusing on a very interesting topic about our planet. So we will be studying earthquakes. Now before we go into the details of our lesson on earthquakes, I want all of you to focus your attention on this map of the earth. Now those red markings, those red dots, they indicate occurrences of earthquakes. And if you will analyze this map, most earthquakes worldwide, they occur along plate boundaries. Okay? So most earthquakes worldwide occur along those plate boundaries. Now, what is an earthquake anyway? Now, by definition, an earthquake is the shaking of the earth. And this is due to the movement of rocks along a plate boundary or fault, as I have mentioned a while ago. Now, most earthquakes, they occur along plate boundaries or fault lines. And when rocks are moving on a plate boundary, they are subjected to stress and strain. Rocks are subjected to stress and they accumulate strain energy over time. Okay, so everybody, I want you to zoom in on this diagram explaining what happens before an earthquake occurs. Okay, so when rocks move along plate boundaries, they are subjected to extreme strain and stress. So if that happens, rocks get deformed. So before that movement of the tectonic plates, the rocks are undeformed. But when these tectonic plates, they begin to move, these rocks are subjected to stress and strain. And when that happens, rocks, they get deformed. There are two types of deformation of rocks. So we have brittle deformation, wherein there is faulting, and we have ductile deformation, wherein there is stretching of the rocks. So that's what happens before an earthquake can occur. Ngayon, para mas maintindihan pa ho natin kung ano ang nangyayari bago mag-occur ang isang earthquake, ito na lang po ang isipin natin. That the Earth's crust is broken into sections or tinatawag natin na tectonic plates. And these tectonic plates, they are floating in that part of the upper mantle called the asthenosphere. So, ang ibig lang sabihin yan na ang mga tectonic plates na yan, they exhibit movement. Gumagalaw po yung mga tectonic plates na yan. At pag gumalaw yung mga tectonic plates na yan, yung mga bato along the plate boundary, they are subjected to a certain amount of force na tinatawag natin ay stress. Stress is force per unit area. Now, itong stress na ito can be tensional stress. Okay, take note, tensional stress. Ang ibig lang sabihin yan, yung mga bato, they are pulled apart. Or pwede rin pong compressional stress. Pag sinabi natin compressional stress, nai-squeeze po yung mga bato. And when that happens, the rocks are subjected to strain. So if the rocks are subjected to stress, nai-strain po yung mga bato. Ano ibig sabihin ng strain? Yung strain is the tendency of the rocks to change shape. So unti-unti ho nagbabago yung shape ng mga bato. At ito yung tinatawag tinatawag po natin na deformation. Strain will lead eventually to the deformation of the rock. So nagbabago po yung shape ng mga bato. Now, this deformation of the rocks can be either brittle deformation, as in the case of faulting, so nahati po yung mga bato as in the case of faulting, or we have ductile deformation na i-stretch po yung mga bato. Ngayon, baka tanungin ninyo, ano naman ang kinalaman ng stress, strain, and deformation sa earthquakes? Now, we all know that when these tectonic plates move, the rocks are subjected to stress or yung force per unit area. Now, when this force continues, the rocks, they get strained. So, ibig sabihin nito, unti-unti po nagbabago yung shape ng bato. And when that happens, nadideform po yung mga bato. Now, when stress eventually exceeds the strength of the rocks, ano po nangyayari? The rocks break. Okay? When stress exceeds the strength of the rocks break. Okay? And it releases energy. So, pag nag-break po yung bato, that releases energy. We call it strain energy. So, this strain energy is released as seismic waves. And the longer that energy is stored up and is maintained without release, the more likely that a strong earthquake will occur. Ngayon, para mas umaunawaan po ninyo kung ano yung ibig kong sabihin dito, that when stress exceeds the strength of the rocks break and strain energy is released as seismic waves, ito na lang po ang isipin natin. Now, I have with me a plastic spoon. Okay? So, ang gagawin ko dito, I will subject this plastic spoon to a certain amount of force. So, bibigyan ko po itong plastic spoon ng stress as I apply a certain amount of force. So, here we go. So, I am now applying a certain amount of force or stress onto the plastic spoon. So, ano pong napapansin ninyo as I apply stress onto the plastic spoon? So, you will notice that the plastic spoon slowly bends. Nagbe-bend po siya or nagbabago ngayon siya ng shape. So, this is what we call as strain. This plastic spoon is under strain. Kasi po habang ina-apply ko ng force, yung spoon na ito, nagbabago na po yung shape ng spoon, nagbe-bend na po siya. So the spoon is under strain. Now, when the stress exceeds the strength of the plastic spoon, ano po ang mangyayari? So I will now continue to apply force onto the plastic spoon. So I will continue to provide stress and strain to this material, and look what will happen. So ganito po yung mangyayari. So the bending continues. Alright, and slowly, yun. Did you hear that? Diba? So nagkaroon ng cracking sound habang nag-break po yung material, tong plastic spoon. So when the stress exceeds the strength of the material breaks. And nag-release po siya ng sound. Okay, yun yung energy na na-release as the rocks or the material breaks. So isn't that fascinating? So it's the same with rocks. So when the stress exceeds the strength of the rocks break. So parang yung nangyari dun sa kutsara, sa plastic spoon. So when the stress exceeds the strength of the plastic spoon, so ano nangyari? Nabali po yung plastic spoon. And narinig nyo po yung cracking sound. So it's the same with rocks. So when the rocks break, they release strain energy. So kagaya po ng sound energy na na-release nung nabali yung plastic spoon. And this strain energy is released as as seismic waves. Okay? And the longer that energy is stored up and is maintained without release, the more likely that a strong earthquake will occur. Okay? So everybody kindly take a look at this animated illustration. So as you could see here, the rocks are subjected to stress. And pag nangyari yan, nagbe-bend po. The rocks are deformed. And pag nag-deform yan, if the deformation continues, those rocks will break. Okay? So, and when that breaks, it's probable that an earthquake will occur. Now, everybody, I want you to take a look at this animated illustration. So, as you could see here, the rocks are subjected to stress. And when that stress continues, the rocks get strained, or slowly the rocks changes shape. And when this continues, the stress will eventually exceed the strength of the rocks and the rocks will break. And when the rocks break, they release energy in the form of seismic waves. So that's how an earthquake occurs. Alright? So, when rocks are subjected to force and shape, that stress and strain, they accumulate energy and slowly they get deformed until their internal strength is exceeded. At that time, a sudden movement occurs along the fault, releasing that accumulated energy, and the rocks snap back to their original undeformed shape. So, nag-break po yung bato. Now, this explanation is what we call as the elastic rebound theory. Now, to further explain what the elastic rebound theory really means, let's take a look at this illustration. So, everybody, kindly take a look at letter A. So, the rocks under letter A, they are subjected to stress. Again, stress is force per unit area. And when that stress continues, the rocks, they get strained. Everybody, can you take a look at letter B? So there, the rocks under letter B, they are subjected to stress and eventually the rocks get strained. Meaning that slowly the rocks change shape or they get deformed. Now, as the deformation continues, eventually, the stress will exceed the strength of the rocks. And look at letter C, the rocks will eventually break. Okay? So, this is what we call the elastic rebound theory. And as the rocks break, it releases energy in the form of seismic waves. So that's how an earthquake occurs. Alright, can you take a look again at this animated illustration? So here, the rocks are subjected to stress. Okay? And as the stress continues, the rocks, they deform. So they are under strain. And eventually, when the stress exceeds the strength of the rocks breaks, releasing energy in the form of seismic waves. So that's how an earthquake occurs. Alright? So before we continue, let us now zoom in on these terms, epicenter and focus. Now, what's the difference between epicenter and focus? These are terms that we usually hear in social media and in television every time an earthquake occurs. Now, focus is that point where an earthquake or an underground explosion originates. So, when the rocks break and they release seismic energy, that point where that seismic energy is released or the point where the earthquake originates is the focus. Now, what about the epicenter of an earthquake? Now, the epicenter of an earthquake is the point on the Earth's surface that is directly above the focus. So, as you could see here in this illustration, the point where the earthquake originates is the focus. That's where the release of seismic energy occurs, and that point directly above the focus is the epicenter. Okay, so again, here is the focus where the earthquake originates, and that point directly above the focus is the epicenter. Alright, so I hope everything is clear about the difference between focus and epicenter. Now, at this point, let us now identify the types of seismic waves. The first type of seismic wave is known as the P wave. Now, what is this P wave? Now, the P wave is said to be the fastest kind of seismic wave. And being the fastest, it is the first to be detected or the first to arrive at a seismic station. The P wave can move through solid rock and fluids, just like water or the liquid layers of the earth. And this type of wave pushes and pulls the rocks as it moves through it, just like sound waves pushing and pulling the air. And this type of wave is also known as compressional waves. P waves are also known as compressional waves because of this pushing and pulling of the rocks, just like sound waves pushing and pulling the air molecules as it moves through it. Okay, so that's how we describe the P wave. Okay, so here is a seismogram of the P wave. So the P wave is the fastest, and it is the first to be detected by a seismic station. And everybody, kindly take a look at the movement of the P wave. So the P wave basically pushes and pulls the rock layers as it moves through it. And this is what we call as compressional wave. P waves are also known as compressional waves, just like sound waves pushing and pulling the air molecules as it moves through it. Okay, so that's how we describe the P wave. Now, everybody, I want you to focus on that black square at the middle of our illustration. So, if you will notice, as the P wave moves through that medium, look at the black square. So, the black square gets compressed and stretched. Okay, so this type of wave is known as a compressional wave. So that's the major characteristic of a P wave. A P wave is actually a compressional wave that pulls and pushes the rocks as it moves through it. Alright, so that's the P wave. Now, to help you visualize what the P wave is, let's take a look at this animated illustration. Now, the P wave is also known as the primary wave. Primary because, being the fastest, the P wave is the first to be detected or the first to arrive at a seismic station. And the P wave is also known as compressional wave. Now, as you could see in this illustration, as the P wave moves through rocks, there is pulling and pushing motion of the rock particles. Okay, so as the P wave moves through rocks, there is pulling and pushing motion of the rock particles. So there is initial damage of property as the P wave moves through rocks because there is pushing and pulling of the rock particles. Okay, so P waves are primary waves and they cause the initial rumbling and shaking of the earth. Now, the second type of seismic wave is known as the secondary wave or the S wave, or sometimes this is known as shear waves. Now, the secondary or the S wave is the second wave that you feel in an earthquake. So remember, the first wave that you feel in an earthquake is the P wave being the fastest, while the second wave that you feel in an earthquake is the secondary or the S wave. Now, the S wave is somewhat slower as compared to the P wave, and the S wave can only move through solid rock, not through any fluid medium, in contrast to the P wave. The P wave can move through both solid rock and any fluid medium. And the S wave move rock particles, take note, up and down or side to side, perpendicular to the direction that the wave is traveling in. In contrast to the P wave, remember, the P wave pushes and pulls the rock particles as it moves along the rock medium. Okay? Alright, so that's how we describe the S wave. Now again, look at this recording. So the S wave is the second wave that you feel in an earthquake. And if you will look at the movement of the S wave, the rock particles, they move either up and down or side to side. Okay, so everybody, kindly take a look at this animated illustration. So as the secondary wave moves through solid rock, look at the rock particles. The rock particles, they move up and down or side to side. So that's how we describe the movement of the rock particles as the secondary wave moves through the rock medium. Okay, so that's how we describe the S wave or the secondary wave. And again, as you could see in this animated illustration, as the S wave moves through the rock medium, it moves the rock particles up and down or side to side. Okay? So again, as the S wave moves through the rock medium, as you could see in this animation, the rock particles, they move either up and down or side to side. Okay, so the S wave, they come after the P wave and causes up and down and side to side movement, and this movement of the ground can cause a lot of shaking and lots of damage to property. Okay, so the next type of seismic wave is known as the surface waves or Rayleigh waves. Now, traveling only through the crust, surface waves are of a lower frequency than the body waves, and they are easily distinguished on a seismogram as a result. And though they arrive after the S waves, it is the surface waves that are almost entirely responsible for the damage and destruction associated with earthquakes. Now, let's take a look at this seismogram recording of an earthquake. So the first wave that would be detected by the seismic station would be the P wave. This is followed by the S wave. And after the S wave, the surface waves or the Rayleigh waves would be detected by the seismic station. Now everybody, I want you to zoom in on this animated illustration that would describe the movement of the rock particles as the surface waves would travel along the rock medium. So if you will notice the movement of the rock particles, they move in somewhat a circular pattern, okay, or there is rolling motion of the rock particles. So that's how we describe the movement of the rocks as the surface waves travel through the rock medium. So that's how we describe the movement of the rock particles as the surface waves travel through the rock medium. So again, if you will take a look at this animated illustration, the rock particles, they exhibit some sort of a circular movement, or there is rolling motion of those rock particles. Okay, so everybody kindly focus your attention on that blue dot at the middle of our animated illustration. So as the surface waves travel through the rock medium, look at the blue dot. The blue dot exhibits circular movement, or there is rolling motion of the blue dot. So that's how we describe the movement of the rock particles as the surface waves travel through the rock medium. Okay, and this will do more damage as compared to the S wave and the primary wave. Okay? Alright, so those are the seismic waves of an earthquake. Alright, so I hope marami po kayong natutunan dito sa bahagi ng ating lesson about earthquakes. So kung maalala ninyo, pinag-usapan natin kung ano ang earthquake, what is an earthquake, and what causes an earthquake. So piniliwanag ko po yung elastic rebound theory of earthquakes. Okay, so that's how earthquakes occur. So we can explain the occurrence of an earthquake through the elastic rebound theory. And also, we were able to differentiate between an epicenter and focus. And we were able to identify the different types of seismic waves. So siguro sa puntong ito, dapat nating tanungin, paano ba natin mine-measure ang earthquake? Alright, so let's continue with our lesson. Let's watch this. Now, let's study how we measure earthquakes. Now, the science that deals with the study of earthquakes is called seismology. And the scientists that studies earthquakes, they are called seismologists. And seismologists, they measure earthquakes using instruments called seismographs. Seismographs, these are instruments that record seismic waves or earthquake waves. Then these ground motions or these seismic waves are recorded in what we call a seismogram. Seismograms are traces of amplified, electronically recorded ground motion that is made by the seismograph. Now, everybody, I want you to zoom in on this animation of a seismograph. Now, this seismograph is firmly fixed on the ground, and as the ground shakes, as the ground moves, it also moves that weight, as you could see in that illustration. Now, there is a pen attached to that weight. So, as the ground moves, the weight moves, and the pen also moves. The motion of the pen is then recorded on that revolving drum with a piece of paper. Now, that revolving drum is known as a seismogram. Now, that piece of paper on the revolving drum of the seismograph is known as a seismogram. The seismogram is that paper or graph on the revolving drum created by the seismograph. Now, everybody, I want you to zoom in on this sample seismogram. So, as you could see here, the first wave that is detected is called the P wave. And this is followed by the S wave and the surface wave. So this is how seismologists detect and measure earthquakes through this instrument called the seismograph, and the ground motions are recorded in this piece of paper called the seismogram. Okay, so everybody kindly take a look at this. This is a sample seismograph, and you could see there that piece of paper with the recordings of the seismic waves. So that piece of paper is the seismogram. Alright, so we now know that the seismograph is that instrument that detects seismic waves. Now, the next question is, how do we locate the origin of an earthquake? Or, shall I say, how do we locate the epicenter of an earthquake? Alright, so everybody, let's listen to this and we shall now study how seismologists locate the epicenter of an earthquake. So everybody, listen and watch this. Now, after detecting the presence of the seismic waves using the seismographs, the seismologist needs now to determine the location of the epicenter of an earthquake. Now, in doing so, they need to consider the following. Now, the first thing that the seismologist needs to determine is the distance of the earthquake. The distance of the earthquake must be determined by the seismologist. Now, in doing so, they need to consider the following steps. Alright, number one, the seismographs records the seismic waves. And number two, from the seismograph record called the seismogram, as we mentioned a while ago, that piece of paper on the revolving drum, the seismologist now measures the time delay between the P and the S wave arrival. Then the seismologist will use a travel time curve to determine the distance of the epicenter of an earthquake as a function of the P and S time delay. Now, to help you further understand what this means, let's take a look at this illustration of a seismogram. So, this seismogram has recorded the following seismic waves. So, we have here the P wave, usually that's detected first, then followed by the S wave, then we have the surface waves. Now, seismologists will consider the time delay. So, this time delay is between the P wave and the S wave. So, we call this the SP interval. Alright, so that's what I meant by that time delay. Alright. So, for example, let's say the time interval between the P wave arrival and the S wave arrival is 5 minutes. So, that 5 minutes is our time delay. Okay, then the seismologist will superimpose this seismogram recording to a travel time curve like the one you're seeing right now. So this is what we call a travel time curve. So by superimposing the seismogram recording with this travel time curve and considering the time delay between the P wave and the S wave of let's say 5 minutes, the seismologist can easily determine the distance of the epicenter. Okay, so that's the first thing that the seismologist must determine. The seismologist must determine first the distance of the epicenter. Now, the next thing that they need to determine would be the direction of the epicenter. Now, we know the distance that the seismic waves have traveled, but we don't know yet the direction from which they came. So, they must repeat this activity of determining the distance of the epicenter in at least 3 seismic stations in order to triangulate the epicenter. Okay, so the seismologist will now plot a circle around the seismograph location. Now, the radius of that circle is the distance of the epicenter. Then, the seismologist will do the same thing for at least 3 seismograph stations. Then, the circles will intersect at the epicenter. Okay, so this method is what we call as triangulation. So to help you better understand this process of triangulation, let's take a look at this illustration. So in the triangulation method, we need to consider 3 seismic stations. Okay, so in this example, we have the following seismic stations. So we have seismic station A that is represented by the red dot. Then we have seismic station B that is represented by the blue dot, and we have seismic station C that is represented by the green dot. Then we all know that the first thing that the seismologists must determine would be the distance of the epicenter. They were able to achieve that by considering the time delay between the P wave and the S wave, and using the travel time curve, they were able to determine the distance of the epicenter. So let's say that seismic station A was able to determine the distance of the epicenter to be about 1,500 kilometers. Then let's say seismic station B, they were able to determine the epicenter, the distance of the epicenter to be about 5,600 kilometers. And we have seismic station C, they were able to determine the epicenter, the distance of the epicenter to be about 8,600 kilometers. Then the next thing that the seismologists must plot would be a circle using the distance of the epicenter as the radius of the circle. So seismic station A has that circle. Then the seismologists of seismic station B will also plot their circle, and seismic station C will also plot a circle using their distance from the epicenter as the radius. So we have 3 circles. All right? Then the point where the 3 circles intersect, that is the location of the epicenter of an earthquake. Okay, so isn't that fascinating indeed? Now, let's take a look at this example to further illustrate the procedure called triangulation. So, let's consider this map of the United States. So, let's imagine that there was an earthquake that occurred in the United States. So, in the triangulation method, we need at least 3 seismic stations to triangulate the epicenter. So, the first thing that the seismologists must determine is the distance of the epicenter. So we have here 3 seismic stations, one from Berkeley, the other from Denver, and the other from New York. So they have determined, let's say, the distance of the epicenter using the P and S time delay and the travel time curve. Then the next thing that they need to determine is the direction of the epicenter. So they will plot circles on this map using the distance as the radius of their respective circles. So we have here 3 circles, and where the 3 circles intersect, that is the direction of the epicenter of an earthquake. So this method is called the triangulation method in determining the location of the epicenter of an earthquake. So isn't that fascinating indeed? Okay, so before we continue, let's watch this fascinating video about the triangulation method in determining the location of an earthquake. Alright, so let's watch this.
All right, in the previous videos, we looked at how earthquakes happen, and we looked at the type of seismic waves that are associated with earthquakes. With this one, we're going to look at something called triangulation, and how we know where an earthquake happened, what the magnitude was, how far away it happened. So what we're looking at here, this is an example of a seismogram. All right, so a seismometer or seismograph is an object that records seismic data. It records those vibrations. And you've seen this before in some of the other videos we've watched, but it's got the little needle, and as the earthquake happens, it vibrates like that. It creates something that looks like this. Well, so I want to kind of show you a little bit about how we read this. Right? As the needle's going along the drum, along the paper there, or whatever, and the needle starts to vibrate as soon as the first seismic waves arrive. Now, P waves are going to be, or primary waves, are going to be the first waves that show up. The first waves that a seismograph will record, because P waves travel the fastest. Okay? They are longitudinal waves, as we said before, and they do travel the fastest, so they're going to arrive first. All right, so what happens is, we see right here, all right, the vibrations come, the P waves really come through right here, and all of a sudden they pass and they subside. And then you notice that it starts to go again. Well, this is the arrival of the S waves, or the secondary waves. All right, so in order to determine how far away an earthquake happens, we measure the time interval between the arrival of the P waves and the arrival of the S waves. All right, and this one today it's done, on computers and whatnot, and they can get down to milliseconds and nanoseconds and whatever seconds it is, and there's a formula. We know how fast P travels, we know how fast S travels. So we can measure the time gap between these two, and that'll tell us a distance, right? Because speed equals distance divided by time, so distance equals, well, you should know the formula. Exactly. D equals VT. So if we know the speed and we know the time, we can figure out the distance. Is that correct? All right, so we can figure out the distance. Okay, so but the only thing that tells us is how far away the earthquake is. So let's say that we're here in the University of South Carolina, right down the road, and the seismograph goes off and it records that there's an earthquake, and it records the P waves, it records the S waves, and they measure the difference in the time between the arrival of P and the arrival of S, and we calculate how far away that is, and we know that the earthquake happened 3,000 kilometers away. Well, that's great. In what direction? Well, see, there's the problem, is that if we're only using one seismic station, if we were only using the seismometers over USC, then we would only be able to find out that it was so many miles or so many kilometers away, but that wouldn't tell us what direction. It's north, south, east, west, whatever. So we're going to use something called triangulation. Okay? The triangulation, we're going to use at least a minimum of seismic data from three different seismic stations. Now, in reality, you're going to use a lot more than that, because the more seismic stations you use, the more accurate it's going to be. But we're going to do this, and we're going to show that there are three. So here's the United States. We're looking at triangulation. Triangulation is really, really simple. All right, so let me show you. Give me three different colors here. Okay. Let's say that an earthquake happens. All right, and let's say that this seismic station right here in South Dakota, that it registers the earthquake, and it measures the time interval between the arrival of P and the arrival of S, and it finds out that the earthquake happened 400 miles away. Well, what you do is you draw a circle around that seismic station that has a radius of 400 miles. Okay? And let's say that this seismic station over here in Colorado, let's say that it registered the earthquake, and the distance is determined based on the arrival of P and the arrival of S, and they came up with, let's say, 300-mile distance. All right, so we're going to draw a circle around this one with a radius of 300 miles. Yes, I know my circles are not perfect. Deal with it. This is not art class. Okay? And let's say that over here in California, at their seismic station, whatever this happens to be, and let's say that they measure the distance of this earthquake at being 700 kilometers. Okay? Well, I'm going to go off my board here, but all right, there we go. and that radius is 700 I said miles, 700 miles away. All right, well, if you notice, these three circles intersect each other at only one point, right here. At that spot right there, where those three circles intersect each other, is the epicenter of the earthquake. It's just that simple. Okay? That's why you have to have three. Because if I only have two, well, the blue one and the green one, they intersect here and here. Well, that's two different spots. We're not really sure. Well, if we use a third one, bada bing, bada boom, bada boop, there you go. They intersect. We'll do it again over here. All right? So let's say up here in New England, I have one, and it's whatever miles away. I don't know. What do you want to call that? 500. Okay, 500 miles away. All right, and over here in Ohio, it's whatever we'll call that, 400 miles away. All right. Now notice I've only used two seismic stations. One up here, I guess, what is that? New York, New Hampshire, whatever. This one over here in Ohio. I'm intersecting at two spots. Well, that's no good. That's only two spots. I got to narrow that down. So I'm going to narrow that down by using the one here in South Carolina. All right, there we go. My radius is what, let's say 600. It doesn't matter. I'm not drawing this to scale. All right. Well, these three intersect at only one spot, right there. That's the epicenter of my earthquake. It's just that simple. It's called triangulation. All right. It's the same concept that law enforcement use when they're trying to figure out where you're making that call from when they're pinging things off cell phone towers and whatnot. So triangulation is not just for earthquakes. It's used, a lot in locating objects in law enforcement, homeland security, and various other things, I'm sure. But anyway, triangulation, that's how we locate the epicenter of an earthquake. Great.
Now, isn't that fascinating about triangulation as a method of determining the epicenter of an earthquake? Now, another thing that we need to consider in our study of earthquakes would be the difference between magnitude and intensity. Now, these are the terms that we usually hear every time an earthquake occurs. So, ito yung mga naririnig natin sa radyo, sa TV. Ano ba ang magnitude ng lindol? Ano ba ang intensity ng lindol? Okay, so let us now differentiate between magnitude and intensity. Now, when we speak of magnitude, the magnitude of an earthquake refers to the measure of energy release during an earthquake. Or in short, ito yung tinatawag natin yung lakas ng lindol. And we usually measure the magnitude of an earthquake using the Richter scale. Okay, the Richter scale was named for the renowned seismologist Charles Richter. Okay, so to give you an idea of the Richter scale, so kindly zoom in on this table. So this table is the Richter scale with the corresponding consequences or damages. So for example, if the earthquake has a magnitude of 3 to 3.9, if you will look at this table, so there's little damage, but it is felt by most people. Okay, then if the earthquake has a magnitude of 5 to 5.9, so there is minor damage to poorly designed buildings, lalo na pag yung bahay o yung building ay gawa sa substandard materials. So giba yan pag ang earthquake ay nasa magnitude 5 to 5.9. Okay, if the earthquake has a magnitude of 6 to 6.9, there is serious damage over a 100 kilometer area or less. Okay, so habang tumataas yung magnitude, we could see more damages to property and probably the more lives would be taken. Okay, so that is the Richter scale. Now, what about intensity? So when we speak of intensity, the intensity of an earthquake refers to the amount of damage done in an earthquake. And we usually measure the intensity of an earthquake using a special scale known as the Mercalli scale. The Mercalli scale is used to express damage done by an earthquake. Now, everybody, I want you to zoom in on this table. So this table represents the Mercalli scale in measuring earthquake intensity. So in this table, we have intensity 1 earthquake up to intensity 12 earthquake. So intensity 1, that's instrumental, detected only by seismographs, while look at intensity 12. So intensity 12 is catastrophic and there is total destruction. So that's the Mercalli scale in measuring the damage done by an earthquake, and we call that intensity. Intensity is a measure of damage done by an earthquake. Well, I guess that's about it for our discussion on earthquakes. So I hope marami po kayong natutunan sa ating lecture, and sana po sa pamamagitan nitong lecture na ito on earthquakes mas magiging handa po tayo kapag may dumating na lindol. We should always do duck, cover, and hold pag may dumating po na lindol. Okay, so hindi po natin mapepredict kung kailan dadating ang lindol. There is no way to predict earthquakes. So dapat po lagi tayong maging handa at alisto. Okay, so if you like this lecture, please subscribe to my channel and please click on the notification bell para ma-update po kayo sa aking mga future videos. Alright, so this is the Science Guy, June Cajigal, saying live long and prosper and always stay safe. So magandang gabi po and thank you very much. Goodbye.